what we would have to do is create a rectangular approximation that could be used to find the area under the curve, right? Now, the one thing, I mean, pre-printed graphs are wonderful, but the one thing I kind of regret is that I never took you through actually constructing the diagram by hand. So what I'm going to do, just kind of off on the side here, is just a very quick sketch of what I mean by left to right and right to left. So because the diagram's already, it's already a static thing, there was never any kind of instance where we kind of saw where it came from. So I'm just going to do that real quick. So when we look at something like f of x equals x squared, we know it's going to be a parabola. We know it's going to happen over the interval of 0 to 2. That's only because they said so, right? But what we can do is we can use rectangles to approximate the area under this curve, right? But the thing is, because the curve itself isn't horizontal, it's not going to be a perfect fit, right? So if I want to create rectangles that are going to approximate this area, there's really only two ways that I could do it. One way would be to start on the left side with that leftmost point, plot a point on the curve, and draw a rectangle with that being the upper left-hand corner of the rectangle itself. All right, so I would do something like this. Well, this one would have a rectangle with no height. All right, so that's not telling us much of anything. All right, but then I could create another point and let that be the upper left-hand corner of the curve. And actually, as I'm looking at my diagram, I think I might have actually put them backwards. So that's aggravating for me anyway. So, but I'll fix that in a minute. So I could plot another point, create another rectangle, another point, create another rectangle, another point, create another rectangle, and so on. So 1, 2, 3, 4, 5, 6. Another point, another rectangle, another point, another rectangle. And so what I have here is an underestimate. All right. I created rectangles that would fit the curve. Now, ideally, they would be, I thought I was being cute by pre-printing the graphs so that I would have actually something that looked halfway decent. But the reality is, I'll find a way to screw it up no matter how I do it. But these are supposed to be of even width, right? So the area under each of these rectangles, the area under each of these rectangles should add together to give us an approximation of the area under the curve, but the width of each rectangle should be the same, right? So each one of these widths should be the same, even though it looks a little skinnier off at the end, it really should be a little bit wider, all right? But that's the idea, and what we call this is the left rectangular approximation, all right? But they throw the word method on at the end so that you can make it like an acronym, like LRAM. So we would call this LRAM, left rectangular approximation method. All right. And that's only because the point corresponding to the curve is the upper left-hand corner of the rectangle. All right. Yep, totally got that backwards. Let me just do something real quick. Copy. Paste. That in a minute. All right, well, that's a typo for somebody. My loss is your gain, I guess. Don't take advantage of those typos, folks. Just a reminder, all you have to do is send me an email saying, there's a typo on this page, here's the typo. And if it's not obvious how to fix it, then make a brief statement on how to fix it. But it's really just, in this case, graphs are backwards on page 66, and I'll know what that means. Because just because I'm fixing it here doesn't mean it's going to get fixed in my master document. And so next semester, I'm going to be running into the same problem. And so that's where you end up helping me. All right. But that's an idea of where the LRAM comes from. All right. All right. So then if I wanted to do it from the right-hand side, it would be the same idea, except I would start my graph instead of on the left, I'd start it on the right. All right. So I would take a point, I'll make it blue, plot it at 2 instead of at 0, create a rectangle, and work my way over to the right. And each one of these points on the curve would be the upper right-hand corner of the rectangle. All right, and so that would be an RRAM situation. All right, right rectangular approximation. All right, so I just wanted to take a minute and walk you through that, because I felt like it's definitely an important piece of information, but I felt like the pre-printed graph doesn't really get that across as much as physically doing it at least one time. All right. So anyway, let me just resize this a little bit. For this situation here, we're working with 8 subintervals, right? So we know that whether we're working from left to right or right to left, we're going to have 8 rectangles, right? Beginning at 0 and ending at 2. Won't always be 0 and 2 as the beginning and ends. It's just saying here between 0 and 2, right? So if I break this interval up into 8 evenly spaced increments, halfway in between, I'd have a 1. Half of that would be 1/2. We'd have a quarter. Would be a 3/4. So we know the spacing for each increment would be 1/4. So that's my delta x, right? And we can label all the values here, because we need these values anyway. So why not, right? So this would be 5/4, 6/4 or 3/2, 7/4, 8/4, which is equal to 2. But each increment is equal to 1/4. So delta x is 1/4. We talked about this last time. We could also find the difference between the b and a value and divide it by the n value, right? So that's 2 minus 0 over 8, which would be 1/4. All right, so it'd be the same set of values on the x-axis for the other diagram, which is why I needed it to be somewhat around the same size so that this would match up. Close enough. This I can kind of scooch over a little. All right. So when I say values on the x-axis used to find rectangle areas, I'd be looking at, just focusing in on the left-hand side, I'd be saying, all right, well, what points on the x-axis were used to find the height of the rectangle? And by that, I mean, what is the x value that corresponds with a point on the graph? And that point on the graph would have to be the upper left-hand corner of the rectangle. So I would have this point here, this point here, this one here, this one here, this one here, 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 and here. Basically everything except for that 2 at the end. All right, because that 2, you see the 2 does not go up and connect with the curve. All right, so we would ignore that last one. All right, every other point gives us a height. Now, one of them gives us no height, like a height of 0, but it's still something that would, in theory, be a rectangle. All right, 1/4 gives us a height, 1/2 gives us a height, 3/4 gives us a height, 1 gives us a height, and so on. All these values give us a height along the curve, right? A height corresponding to the rectangle, right? So then we would just want to figure out what those heights are, since we know that it's y equals f of x equals x squared. And so the function of x is equal to x squared. Each y value is whatever you get when you pop in the x value for x squared. We know that the heights are going to just be whatever the y values are. So the coordinates are really what we're after here. 0, 0. This is going to get a little tight, so I'm going to write it smaller. And I'll do it in red. 0, 0. 1/4, 1/16, 1/2, 1/4, 3/4, 9/16, and so on up the line. 1, 1, 5/4, 25/16, 3/2, 9/4, 7/4, 49/16. All right, so every one of those coordinates is relevant. There should be a total of 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Each one of those y values represents the height along the curve, or the height of the rectangle along the curve. So for example, if I just highlight like that one, just to give you an idea. All right. So if I take that measure and multiply it by the length of the base, each base has a value of 1/4. I'm going to go with something that'll kind of stand out here. See if this, no, that's going to be too bright. Go with like an orange. Nope. Go with the classic red. Go with the classic red. Keep it simple. So the base is 1/4. The height for this one, for example, is 49/16. We could figure out the area of this rectangle. The base is 1/4. The height is 9/4. We could find the area of that rectangle. All right, and so on. We go through and we could do it all that way. All right, but that's a technique that would help us figure out just this one problem. We need something that's going to help us figure out any problem of this variety. All right, which is why, oh, you get the y values by plugging in the x values into the original function. The original function is f of x equals x squared. So if you take each one of these values and plug it into x squared, f of x is equal to x squared, you get the corresponding y values. All right. So in theory, I did all that correctly. But if you plug in a 0, you should get a 0. 1/4 squared is 1/16. 1/2 squared is 1/4, and so on. All right. So that's why I have this progression, this table progression, because it's supposed to really kind of show you that if we could come up with a rule that would help us determine the x values, then plug those x values into the function and then multiply those x values by delta x, because the delta x is that horizontal distance. All right, each one of these horizontal distances is the delta x. That's where this step in the process comes from. Then once we kind of generalize that, then we can stop working with, well, first off, any finite situations where it's like 8 rectangles, because we know it's not going to give us a reasonable approximation. It'll give us a lower bound, but it's not going to give us, necessarily what we want. Maybe we could do something that'll allow us to get really, really close to the true area under the curve, right? So we carry through this process. Our relevant values are 0, 1/4, 1/2, 3/4, 1, 5/4, 3/2, and 7/4. Because remember, the 2 was irrelevant because it didn't correspond to a point on the curve. All right. Then we plugged each one of the values into the f of x. That gave us the y values, the corresponding values of y. which were 0, 1/16, 1/4, 9/16, 1, 25/16, 9/4, 49/16. Then multiplying each of those values by delta x would give us the area of each individual rectangle. All right. So I could look at this and say, all right, well, just take each one of these values and multiply it by 1/4, or since I got to add them all up later anyway, maybe I just add up all these values and then multiply it by 1/4 later on. All right, so you kind of have a choice in the matter, but we'll follow the instructions. 0, 1/64, 1/16, 9/64, 1/4, 25/64, 9/16, 49/64. Then we add them all up. So really just taking all this stuff and putting a little plus sign in there. All right. So that sum would give us the lower bound of the approximation. All right. And we could crunch that all out in a minute. All right. But we're gonna take care of the other side. But before we do that, let's see if we can kind of generalize this. All right, because what we're looking at here, so for these values, this is a sequence of values. All right. So this sequence of values can we can express this in a couple of different ways, but if we go back to what we were talking about right in the beginning of this unit, well, right after Rolle's theorem and mean value theorem, the summation notation and all that stuff, we get at the idea that we could come up with a rule if there's a distinct pattern to a sequence of values. So here we're starting off with 0, and we're adding to that 1/4 multiplied by something. You know, it's just a question of what that something is. So you can call it I, you can call it N if you want. It really doesn't matter. You just have some sort of placeholder to represent that relationship, right? So if I say that I have, and I could actually just kind of take you back here real quick. That, oh, where do I have it written? The term of a sequence, we would say a sub 1, a sub 2, a sub 3, a sub n. Those represent the progression of values that make up a sequence. So when I said I, we would substitute the values 1 through 6 in for I. I'd get 1, 2, 3, 4, 5, and 6. All right. And then we would add it all up, but we're not quite there yet. All right, but we'll get there in a sec. But what I can say here is 0 plus 1/4 I, right, where I is going to go from 0 to well, this is going to be 0i, 1i, 2i. I'm sorry, 2i. 2 as 2 substituting in for I. So 2 times 1/4, which is 1/2. 3 times 1/4. So 3 goes in for I, which would make it 3/4. 4 goes in for I, which would make it 4/4. 5, 6, all the way up to 7. All right. So that would be an A sub I relationship. All right. A sub I would be equal to, really, I mean, simplify it even more, because that 0 kind of makes things a little on the nicer side. I could say 1/4 times I. All right, 0 plus 1/4 I. If it's going from 0 to 7, then I get all the relevant values. Then we said plug each x into f of x. Well, what I can do here instead, you know, we did it manually, each one of the values, but what I can do is I can plug my A sub I into my function. So it would become f of a sub I. Right? It's kind of a mouthful, but it is what it is. Right? We know f of x, because remember, f of x in this situation is x squared. So f of a sub I would be, instead of x squared, it would be a sub I squared. All right. But we have a rule for a sub I. We know that a sub I is equal to 1/4 I. Right. So I can take this number, the 1/4 I, and square that. And I would get 1/16 I. Still over the same interval. All right. So we test it out. You plug in a 0 for I, you get 0. Plug in a 1 for I, you get 1/16. You plug in a 2 for I. All right. Well, that just kind of fell apart. Hold on 1 second here. Timeout. One. Oh, well, it would help if I actually squared the I, just in case anyone was wondering what happened there. Dingus. Yeah, so 1/4 I, apparently if you square that, it isn't just the 1/4 that gets squared, it's the I also. All right, so brain cramp, apologies for that. Yeah, so if you plug in a 0, you get 0. If you plug in a 1, you get the 1/16. So you plug in a 2, 2 squared is 4, 4/16 is 1/4. Plug in a 3, 3 squared is 9, 9/16, and so on. All right, eventually you plug in the 7, 7 squared gives you 49, 49 over 60. All right. So now, again, multiply, just following the progression, multiply by delta x. All right. So what we would be doing here is taking this f of a sub I and multiplying it by delta x. We just discovered that f of a sub I is the same as 1/16 I squared. All right. So that's a direct substitution. Delta x, we said way earlier, was equal to 1/4. Now, it's not always going to be equal to 1/4, but in this case, it's equal to 1/4. All right, so I'd multiply by 1/4. So I'd get 1/64 I squared. All right, and that would be over the interval of 0 to 7. And again, it's another thing that we can test out real quick. If I plug in a 0 for I get a 0. If I plug in a 1 for I get 1/64. Plug in a 2 for I get 4 over 64, which is 1/16. So it still checks out. All right, the a sub I thing is generalizing this relationship. All right. So what we want to do is we want to come up with a rule that allows us, instead of having to write out each one of these numbers and then plug each one of these numbers into the function and then multiply each one of those values by delta x, what I want to do is come up with a rule for this sequence that would allow me to do it all in one shot. All right. Because this is called an arithmetic sequence. I mean, the name of it really isn't that important, but what happens is you have a steady incremental increase with some starting values. So there's a linear relationship, right? So to write the rule, all you have to do is identify the starting value. So my starting value is 0, and then the incremental increase. So to get from a 0 to a 1/4, we add a 1/4. To get from a 1/4 to a 1/2, we add a 1/4. To get from a 1/2 to 3/4, we add a 1/4. So if we create a multiplier of 1/4, add it onto 0, that can get us to any value within the sequence. We just need to dictate where we're going to start and stop. All right. And that at this point is really just trial and error to say, all right, I have a rule that says 1/4 I. If I replace that with a 0, what do I get? Well, I get a 0. That's good. That's the first value in my sequence. That's what I want. That if I plug a 7 in for I get 7/4. That's my last value. That's what I want. So now I know the bounds of my sequence. And that carries through the whole process. All right. So now that I have a rule that represents a sub I can plug it into the function. Then I can multiply that result by delta x, and I'm developing a generalized rule all the way through that could be applied rather than crunching these numbers individually. I'm crunching the numbers related to just the rule so that the computations become easier, but it's really more than that. This is a technique that's going to allow us to expand beyond just 8 rectangles. What if because right down at the bottom, who wants to do this for 16, 32, and 256 rectangles? That's not the idea. We don't want to do that, right? So we want to come up with a shortcut, and this is building us to that. All right. So the next step in the process was to add all the resulting values together. So that's a summation, right? That summation started off with an I value of 0 and went to a 7, but it's the summation of f of a sub I times delta x. All right. So through direct substitution, because we know f of a sub I times delta x, we just figured that out, is equivalent to this 1/64 I squared. Instead of writing this whole thing, I could instead say the sum from I equals 0 to 7 of I squared over 64, or 1/64 I squared. That would give me the area also. But it's not just restricted to 7 rectangles. All right. So we can modify this. We'd have to go back a step, but we can start thinking about how to modify this in order to end up with something that would be more universal. All right. And that's what we're going to get to in a few minutes. But we also have to do this from the right side. All right. So I could add up all these numbers here. All right. I could take all these numbers and add them together. Or I could use the summation feature in Desmos. All right, so if you go under miscellaneous, we use I. I equals 0, going to 7. So 1/64 times I squared. So 2.1875 approximately. Well, exactly, because that's a decimal value. But that would be our low bound. And that's what you would get if you added up all these values here. All right, so 2.1875. All right. So then from the right to left, it becomes a whole lot easier because we're using a lot of the stuff that we've already figured out, right? So we know that the relevant parts of this diagram are going to start on the right side and work our way to the left. It's going to start off with the point 2, then go down to 7/4, then 3/2, then 5/4, then 1, and so on. But eventually we're going to stop at 1/4 because that gives us the last remaining height. All right, so we have this rectangle, this one, if I can get it to look rectangular, and so on. So all of these rectangles contribute to finding the area for the right rectangular approximation. I'm gonna zoom in big time. With that last one, that last relevant one being at 1/4. If I can get it to land. Just kind of pretend. So I only care about these values. Right? But if we go through the same progression, I mean, we could do it by the numbers, the 1/4, 1/2, and so on, but then we would throw on a 2 at the end. So it's like, all right, well, let me take all these values, but then throw on a 2. But then we also want to be thinking about what that means. Right? So in this case, I'm talking about really it's the same sequence, but I don't want to start off at 0. Right? Because if I use the same rule, of a sub I is equal to 1/4 I. If I start this off at 0, that's going to give me my first entry of 0 rather than a 1/4. But if I start this one off at 1 and then cap it off at 8, then I'll get the sequence of values that I'm looking for. All right, 1/4 I will still do the trick. That same relationship. It's still the same incremental change from value to value, except it's one step further down the line. So instead of going from 0 to 7, I can go from 1 to 8. All right. When I plug it into the function, I'm going to get the same stuff. Right? The same sequence of values, except again, I'm going to throw on an extra value related to the 2 at the end. So if I plug this into f of x, you're plugging it into the f of x equals x squared. I'm just going to square each number. This will become a 4. But it's the same relationship, except instead of going from 0 to 7, it's going from 1 to 8. So then when we multiply each value by delta x, we get the same set of values, except instead of going from 0 to 7, it's going to go from 1 to 8. All right, so that'll give us a 1 off at the end because we're multiplying a 4 by delta x. Delta x is 1/4. And again, this is going to go from 1 to 8. And then we would just add them all up. But again, all that amounts to is taking the same set of values, taking off the 0, but throwing on a 1. If you wanted to do it manually, you just add these up. But in terms of the summation, it's really the same relationship, except instead of going from 0 to 7, you're going from 1 to 8. So it's the same rule, except instead of going from 0 to 7, you're going from 1 to 8. Right, so I said that about 1,000 times already. But that's the idea, is that you're just shifting one unit down the line. Right, so when I want to do this computation in Desmos, I'm just going to change the 0 to 7 to a 1 to 8. And that's going to give me a 3.1875. All right. But if you compare that with what we came up with last time, we had 7/4. So the area would be 7/4 and 50, between 7/4 and 15 quarters. All right. 7/4 is 1.75, 15 quarters is 3.75. It was the same bounded region. All right. We should end up with the same area. But what we're getting here is a higher degree of accuracy. Right? This is telling us that if we increase the number of rectangles, we're going to get a truer estimate of the area, because the previous computations gave us an estimate of the area somewhere between 1.75 and 3.75. Right? But now we brought it in a little bit closer. It's between 2.18 and 3.18, right? Ish. 3.19 and 2.19 and 3.18. Right. So it's a truer estimate of the area. We're narrowing the field. Right. So we're closing in on it. So when I say who wants to do this for n equals 16, n equals 32, n equals 256, I mean, you could see all the work here. You definitely are hoping for a shortcut. But like I said, it's going to get a whole lot uglier before it gets a whole lot nicer. All right. So the next example is just a continuation of this. We're doing, oh, actually, really the continuation? Oh, man. Well, typo, of course. By the graph of f of x equals x squared, between x equals 0 and x equals 2, for general n. All right. For n rectangles. All right. So this is the same progression, except now I want to have any number of rectangles be in existence in that interval. Right. Now the diagram is just a disaster, because how do you draw a variable quantity of rectangles? You really don't. So what we do is we just kind of wing it a little bit. But if we have f of x equals x squared, it's the same diagram. But we could kind of freehand this one a little bit more, because there's really there's not much detail that's going into the graph. But we would come in from the left and we would come in from the right. It's just we kind of trail off a little bit. Right. So what I would say here is, just from the left, I'd start off with a point here at 0. I'd work my way to the right, I'd grab another point, then another point, then another point. I mean, it's just a disaster when I draw, so I'm just doing my best. And then we just kind of do a dot, dot, dot. There's more after that, but that's where it would end. That's in terms of us trying to make this work. Because these could have been much skinnier. I could have gone like this, much skinnier with the rectangles, but this is what I chose to do. Right? Now my delta x, still b minus a over n. My b and a are known to be 2 and 0. Right? So it starts at 0, it ends at 2, but I don't know what my n value is. Right? So all I could say for delta x is that it's 2 over n. All right. But what I can say, if I follow the progression that we used on the previous page, we can come up with a rule rather than trying to come up with each individual points, because there could conceivably be infinitely many values between 0 and 2, right? Depending on what you decide on for n. If you want to let n be equal to infinity, then it's a non-starter, all right? So what we would say here is that we're starting off at 0, and we're going to get another point, another point, another point, another point, another point, but that's all dependent on what n is equal to. All right, so my first value would be 0. My second value would be 2 over n, you know, because I would take that 0 and add to it 2 over n, and that would get me my second value. So that would be 2 over n. Then, well, I'm going to have 2 of those 2 over n's, which is going to be 4 over n, you know, 6 over n, 8 over n, and so on, 10 over n, 12 over n, and so on down the line, all dependent on how many steps I'm going to go, right? So really what I'd be looking at is, like I said, I'm going to have 1 of those 2 over n's, then I'm going to have 2 of those 2 over n's, then I'm going to have 3 of those 2 over n's, 4 of those 2 over n's, and so on. And that's where I get 0, 2 over n, 4 over n, 6 over n, 8 over n, and all the way down the line, right? But that would be my sequence. That's one way to write it, right? But if I want to generalize the rule, I would say a sub I is equal to 0 plus 2 over n times I. All right, where I starts off at 0 and increases without restriction. So I has to be greater than or equal to 0. All right. So if I replace I with a 0, I get a 0. If I replace I with a 1, I get a 2 over n. If I replace I with a 2, I get a 4 over n, and so on. All right. So a simplified form, it's not really much of a simplified form, but I could say 2i over n. Now our function is still f of x is equal to x squared. So I could take each one of these values and square it, but that starts to get a little out of hand. Instead, I'm going to say, all right, I'm going to find f of a sub I, which is going to take my a sub I value, which is 2i over n, and square that. So that's going to be 4i squared over n squared. Still for I greater than or equal to 0. All right, that's in lieu of saying, all right, well, 2 over n squared is 4 over n squared. 4 over n is 16 over n squared. This will do the same thing. Plug in a 0, I get a 0. Plug in a 1, I get 4 over n squared. Plug in a 2, I get the 16 over n squared, and so on. All right. So next up would be f of a sub I times delta x, which is really just taking this result, which is 4i squared over n squared, and multiplying that by my delta x, which is 2 over n. And so that's going to give me a result of 8i squared over n to the third power. All right, still for I greater than or equal to 0. So then next up would be to add all this stuff together. All right, so it says add the resulting values together, and we'll get something. All right, so to add values together, we use a summation. So the sum of f of a sub I times delta x. Now that summation is going to go from 0 to some unknown maximum, right? Well, it all depends on how many rectangles we want to have. In the previous situation, we had 8 rectangles. So that was either 0 to 7 or 1 to 8, right? So this would be 0 to n minus 1 or 1 to n, right? So either way is going to work. But if you think about it, in the previous case, like I said, it's here. We had 8 rectangles, but that corresponded to an upper value of 7, right? Because we were going from 0 to 7. If you count from 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7, that's 8 values, all right? 1 to 8 is 8 values. If I want to do the same thing, I would have to go, if I'm keeping it general, I'd have to go all the way up to the n minus first value, because if I went to the nth value, that would be too much. That would be 1 too many. All right. So that would be one option. And in this case, that would amount to the sum from I equals 0 to n minus 1 of, I'm gonna go purple now for those students at home, of this expression, which is 8i squared over n cubed. All right. So that expression would actually give me an area under the curve, depending on what the value of n is. All right. So if n is equal to, well, we had 8 in a previous problem. I mean, we could use 8. So let's say, for example, let n equal 8. Then that would give us I equals 0 to 7 of 8i squared over, that would be 8 cubed. That would simplify down to an 8 squared on the bottom. And we look at that and compare it to what we have, I equals 0 to 7, 1 over 64i squared, right? It's the same thing, all right? So what we just came up with is the rule, but in a more general form, right? So, and I won't even say let, I'll just say if. If n were equal to 8, then I would have this relationship, which would in turn be equal to what we came up with on the previous page. So 1 over 64 I squared. All right, so we know it's going to work, at least for finite values. We just have to make sure that it's going to work for infinite values. All right, because what I want to come up with is not just a rule that's going to help me get the answer for 8 rectangles. I wanted to do it for like 1,000 rectangles, right? Because the more the more rectangles you have, the more accurate your result is going to be. So let's say, for example, if n were equal to, I'll just do another one. Resize. If n was equal to, I'll do 1,000. I don't know if Desmos is going to let me do it, but I'm going to try. All right, if n were equal to 1,000, it would be I equals 0 to 999. And then on the bottom, so we'd still have the 8i squared on the top, but then I'd have 1,000 cubed. Right, that would not be equivalent to that other expression. Right, so if n were equal to 1,000, that's what the summation would pan out to be. So let me just pop that in, see if Desmos can handle it. I might be getting a little ambitious here, overzealous. Right, so Probably could have just retyped the whole dang thing. 1,000 cubed. All right, so 2.67 is what this is saying that the lower bound of the area would be if I had 1,000 rectangles in there. All right, so we went from a low bound of about 2.1875 to about, so this was about 2.1875. This one is about 2.67, I'll say 07, just to go out the same 4 decimal places. All right. So we have something that's gonna work for large numbers. Now it's just a question of are we getting closer to the real area? I mean, well, yes, but are we close enough to the true? Like, can I walk away now and say, I think that the area is 2 2/3? You know, is that a reasonable assumption that I could make? I have a very large number of rectangles here. Can I now walk away with the comfort of saying that I've closed in on the number of rectangles that I could, you know, possibly fit in there and come up with a reasonable result? Maybe, right? But what we can also do is make this a little bit more general. Put in an n-1 on the upper bound. Keep this as n cubed on the lower bound and make a slider, right? Now make that slider, if you know, you can tap on the slider itself, the low bound. We don't need negative, I mean, I'm not gonna have a negative number of rectangles. So I'll tap on the low bound of that slider, make it 0, and then the upper bound, I'll just make it something really huge. Like, well, I already tried 1,000. Let me make it 10,000. And then I'll go by, instead of going by ones, I'll go by like hundreds. And then see what that gives me. Okay, so if I have 0 rectangles, so n equals 0, 0 subintervals, so 0 rectangles, I'll have a 0 area. Okay, well, I guess. If I have 500 rectangles, I'm going to get an area, an approximate area of about 2.65. All right, 2.66 really. 600, 700. We got up to 1,000. We did that before. All right. Although that looks a little bit different from what I came up with, so I'm wondering if I typed in something wrong. But anyway, if I keep going up further and further down the line, it looks like it's converging on something. If I have 10,000 rectangles in there, it looks like it's closing in on 2.6 repeated. It's just a question of, you know, how close to that 2.6 repeated. You know, is it really going to be that, or is it going to be, you know, like so infinitesimally different that we'll fall into the trap of thinking it's 2 2/3, but it's really not, you know? 999, not 1,000. Oh, yeah. So the upper bound would be 999, but the n value itself that we would put in would have to be at 1,000 because I have the n-1 built into the function itself. All right, so that's the rationale there. So anyway, we have a thought coming in on the right-hand side. All right, so, oh, I think n-. Maybe. I'll have to take another look at that. But if we come in from the right-hand side, we know that everything gets shifts over 1 unit, right? So instead of starting off at I equals 0, we're going to start off at I equals 1, all right? So this expression, all this stuff is going to be the same. Actually, I could do a massive copy paste. So all of this I'm going to take and just kind of shove it over to the other side. But we know that we're going to go with an initial value of I equals 1 rather than I equals 0. Oops, a little too thin there. So when we develop our summation, we can go from 1 to the nth value and say that we have the sum from I equals 1 to n, specifically n, of f of a sub I times delta x, which is going to amount to the sum from I equals 1 to n of, really, again, it's the same expression. So it's 8i squared over n cubed. But just going from 1 to n now. So we shifted 1 unit down the line, right? And we could test it out because, again, if we plug in, if we wanted to go for 8 rectangles, if n is equal to 8, so if n equals 8, I would have the sum from I equals 1 to 8 of 8i squared over 8 cubed, right? So going from 1 to 8, but with the same ratio, right? So that would be the sum from I equals 1 to 8 of 1 over 64 I squared, right? Same thing that we had on the previous page. So that would give us the same result. So we know that we're looking at a rule that's going to work, right? But then we can go after it using the same idea and say, all right, well, let me duplicate this. And instead of having I equals 0 to n minus 1, we can do I equals 1 to n, but with the same relationship. All right. So now for the 1,000th value, we're getting the 2.6707, which I expected before, and that's why you were saying that the 999. It didn't connect with. I didn't connect with that at that moment. But yeah, so for 1,000, I would get 2.6707. As opposed to if I did it for 999 in the other case. I would have gotten the 2.6626. All right. So it gives you the lower and upper bounds, but it's giving us what we expected. But even before that, if I just did it for 8 rectangles, for n equals 8, 3.1875. All right. And we did it for 7 rectangles. I'm sorry, 8 rectangles, but going from 0 to 7, it gave us the 2.1875. All right. So it's the same relationship. It just looks a little, well, a lot funkier. All right. So we're talking approximately, well, actually, it's exactly like I said, for 3.1875. All right, but if I jazz up my n value so that it goes, super high, you see that this is converging on the 2.6 repeated idea also. All right, it's just a question of how high can we go, so maybe not 10,000, maybe 100,000. All right, maybe, well, let's see what it can tolerate. But after a while, it does seem to be convincing evidence that it's getting closer and closer to 2 2/3. Right. So what we want to do, again, is come up with the most general approach for this. Now, if I take my n value and make it larger and larger and larger and larger, regardless of whether I use this formula or this formula, I'm going to get that 2.6 repeated, right? So, you bring it, I'll get rid of this, it's in the way now. But I'm looking at the 0 to n minus 1 versus the 1 to n. And you can see that once you get sufficiently large, the area ends up being approximately the same. And in fact, in this case, they're almost indistinguishable from one another. It's only at the very, very tail end that they're a little bit different, right? But it's pretty convincing evidence that they're going to approach the same value. So what we can do to kind of streamline this even more is tack on a limit, all right? The concept of a limit just never goes away. So we could come up with a generalization using the most efficient means possible to find a rule that could be used to determine the area, but then limit that as n approaches infinity. All right. So this one, here's another typo, should have been x squared. Do the progression here. Hopefully, it was supposed to be, let's generalize more and more as we go, increase the number of rectangles. Then we make it the general number of rectangles, and then we come up with the rule, So anyway, so find the area of the region bounded by the graph of f of x equals x squared and the x-axis between these two values for general n. So what we can do in the most general form is pretty much what we did before, but actually really, really generalized. All right. So what I would say is, if you have a closed interval from A to B, call this one A and this one B. All right. Closed interval from A to B. What we're going to do is figure out delta x. Delta x is b minus a divided by n, which is 2 over n. All right, in this case. All right, so we're just kind of generalizing what we did previously. Then we figure out a plus I delta x. Right, so the a plus I delta x is 0, in this case, 0 plus I times 2 over n, which is 2i over n. So again, just rehashing what we did on the previous page so they have a nice process without all the extra fluff. All right. F of a plus I delta x is what you would get if you replace the x in your original function with the result of a plus I delta x. The original function is x squared. So a plus I delta x is really 2i over n. We would square that. All right. If this were a different function, we would apply whatever that function is. So if it were x cubed or x to the 8th, then let's say if it was x to the 8th, then it would be 2i over n to the 8th power. It could even be like the sine of x. If it were the sine of x, it would be the sine of 2i over n, which is not something I would ever do to you because it's way more complicated than what we're doing here. But it is possible. All right, so we get 4i squared over n squared. Then we take f of a plus I delta x and multiply it by delta x. So that's the 4i squared over n squared multiplied by 2 over n, which in turn gives us 8i squared over n cubed. All right, so that's where we were. Now, what we would do is at this point, we would take the sum of that from I equals 1 to n, but there's some other skills that need to come into play in order to be able to get to the point where we can find the limit. All right. So what we're going to do again is find the sum from I equals 1 to n of f of a plus I delta x multiplied by delta x, which in turn is really the same as saying the sum from I equals 1 to n of 8i squared over n cubed. Right, so this is what we have to evaluate. Right, we have to be able to apply a limit to this. Right, the limit as n approaches infinity. Right, so if I were to try to do this, I mean, we'd have the n cubed on the bottom, and that's all well and good, but I would need the sum from I equals 1 to n of 8i cubed, I squared. Right. Fortunately, and it was something I glossed over at the time, saying that it would come back and it'd be really important later on. Now's that moment, but there's something previously in the notes that's going to save us, right? But before we get to that, one thing I can tell you is, since the variable that's relevant to this summation is I, nothing else really needs to be there. So if it can be factored out, it should be. So I'm going to factor out an 8 and an n cubed. All right. So this would be 8 over n cubed times the sum from I equals 1 to n of I squared. This means the same thing. All right. These two are equivalent. All right. So the thing that varies within the summation is the I. That needs to stay. Everything else can go. So then, if you look back a bunch of pages in the packet, you'll see that there's actually a rule for this. There's a rule. And that's going to make everything so much nicer. Right? So I'll draw your attention to that real quick. Right on the bottom of page 63, we have this rule here. The sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. All right. It's a nice rule. I mean, it's a little messy, but it's going to allow us to get out of the summation and go with something that's ordinarily algebraic. All right. So this rule, so again, page 63, is going to come into play now. All right. So page 63. So this is going to be equivalent to 8 over n cubed times n plus 1 times 2n plus 1 all over 6. All right. Now we can simplify this a little bit. I mean, not a whole heck of a lot, but enough to be able to do some work with it. All right. So 6 goes into 8. Well, not evenly, but they're both divisible by 2. So 4/3. N goes into n cubed n squared times. So I'm going to just kind of slide this up to the top here and carry it out from there. So little housekeeping. I'm going to have 4 times n plus 1 times 2n plus 1 over 3n squared. All right, little distributive property. All right, I could hang on to the 4, but when I distribute out these two, I'm going to get 2n squared. Outers would be n, inners would be 2n, so 3n plus 1 times the 4 over 3n squared. which is going to give me 8n squared plus 12n plus 4 over 3n squared. All right. So then the final step, which in and of itself has its own issues, involves us finding the limit of this as n approaches infinity. So we're going to find the limit as n approaches infinity of this. Now, if I plug in infinity into the top and bottom, I'm going to get infinity over infinity. That's an indeterminate form, right? Which means L'Hopital's rule applies. All right, so indeterminate, I cannot fit that in there. Indeterminate. L'Hopital's rule applies. IES. All right, which tells me that if I take the derivative of the top and the bottom separately, I could find the result of this limit, right? Just by reapplying the limit after the fact, right? So I'm looking at 16n plus 12 over 6n. Again, applying the limit as n approaches infinity. We've got a second level to L'Hopital here. It's an indeterminate form. So L'Hopital's rule applies. So we just got to do it the one more time and it will be good. Because once we take the derivative that one more time, it'll go down to being constant on the top and the bottom. So then that'll take care of everything, right? But as usual, I just kind of cut myself short on space here. So let me resize. All right, so take the derivative of the top and bottom separately from one another. And we'd be looking at the limit as n approaches infinity. This would be 16 over 6. Limit of a constant is a constant. 16 over 6 would be the limit, which would be 8/3, or maybe more familiar, I can't even speak, familiarly, I'm going to give up on that word. More recognizably, like Porky Pig here, 2 2/3, right? So 8/3, 2 2/3. So we get the same result that we got computationally, but this time we got it using a limit process, right? But this is the foundation. This is known as a Riemann sum, but this is the foundation of something called a definite integral, right? And so this will give us the area of the curve, or bounded by the curve in the x-axis over an interval, right? But the more you go through this technique, the easier it becomes, because it's pretty predictable, especially for polynomial functions, right? So, you know, in number 5, it says find the area under the graph of y equals 1 minus x squared. Right, so at long last, we're changing up the function. But you could take a quick look at the picture. 1 minus x squared looks like that over the interval of -1 to 1. So it's really just this piece here. I want the area under that curve, right? So it's really saying go from -1 to 1 instead of from 0 to 2, but it's still a parabola. Now, fortunately, we could take advantage of things like symmetry, right? Because when you're dealing with symmetrical curves, you have the benefit of knowing that you, if you find the area of one part, you're going to find the area of the other part, right? So instead of saying go from -1 to 1, why not go from 0 to 1 and then double your answer, right? So that would be, let's see if I can actually graph this. Duplicate. Oops. That would be just this part. So if we find the area of just that piece and double it, then we'll have what we're looking for. All right. So I would modify this by saying find the area under the graph of y, it's still y equals 1 minus x squared over the interval of 0 to 1 and double the answer. All right. So if I'm doing that, I would just do a quick rough sketch here. You know, nothing too crazy. I have my little curve here. It goes from 0 to 1. Here's my A. Here's my B. Poor quality B. Well, poor quality circle around the B. Right? But I would just go through the same progression. So my delta x is B minus A over N. All right. So 1 minus 0 over N is 1 over N. A plus I delta x. My A value is 0 plus I times 1 over N is going to be I over N. Now my function f of x is equal to 1 minus x squared. All right, so just kind of keeping that in mind, because my next step is to find f of a plus I delta x, which means take the x value in your function and replace it with a plus I delta x, which in this case is I over N. So then we would simplify being the word of the day. The 1 minus I squared over N squared when I simplify that, I would get a common denominator, you know, just to make life a little easier, because I'm going to have to multiply this by delta x in a minute anyway. So this would be the same as saying n squared over n squared minus I squared over n squared, which would become n squared minus I squared over n squared. All right, so all of that, all right, well, really any part of that is equivalent to f of a plus I delta x. But like I said, in the next step of the process, we have to take that and multiply it by delta x. So it kind of makes sense to have this in the most simplified form. So we're looking at n squared minus I squared over n cubed. So then we take that and find the sum as I equals 1, or goes from 1 to n, of n squared minus I squared over n cubed. All right, because it's really the sum of this that we're looking for. I guess I could throw that in there. Probably should have to begin with. Oops. All right, so if we can evaluate this expression and then apply the limit to it, then we'll be in good shape. So like I said before, the only thing that needs to stay within the summation is the I squared. So I can pull out the n cubed and make it 1 over n cubed times the sum from I equals 1 to n of n squared minus I squared. But then I could also break up that difference and make that two separate summations. So this would become 1 over n cubed times the sum from I equals 1 to n of n squared. So I'll put a little square bracket here, minus the sum from I equals 1 to n of I squared. One of which is a rule. We've already talked about that rule. We'll take care of that again in a second. But this other piece looks kind of weird because we have an n squared that doesn't really need to be there. So that could actually be factored out of this summation. So I'd still have my 1 over n cubed multiplied by n squared times the sum from I equals 1 to n of just a 1 minus, well, really everything else. So then it's just a matter of, well, doing all the hard algebra. You know, I mean, it is what it is, but it's doable at this point because there's a rule for everything, right? All on page 63. Like this one, I'm going to use pink here, is n times n plus 1 times 2n plus 1 over 6. That looks pretty bad. And then this other piece here, so this one, this doesn't really look like any rule, but I could tell you that there on page 63, there's a constant rule. I don't want to scroll back and forth too many times, but I'll do it in a second. But the very first rule that you see there, I believe it's the sum from I equals 1 to n of c is equal to c times n. That c represents a constant. All right. So let me just show you real quickly. That would be this one. So what this is telling us is that if you have a constant here, all you have to do is multiply it by the upper bound of summation, c times n, and that'll give you the result of that summation. All right. So long story short, in this case, crashed. Coming back. Why it doesn't? I mean, I know why. I'm overworking. Too much math. Come on. You can do it. Well, there's some algebra 1 for you. So this is going to be the 1 multiplied by the n, which is just an n. So we have the 1 over n cubed on the outside, and then we have an n times n squared on the inside, or n squared times n. But this cleans up kind of nicely. It just doesn't seem like it would, you know. So 1 over n cubed times n cubed minus, again, this one was n times, we distributed this one out before, that's 2n squared plus 3n plus 1 all over 6. If we distribute through the 1 over n cubed, we would get 1 minus 2n squared plus 3n plus 1 over 6n. 6n squared, sorry. And so that's what we would need to find the limit of. And once we do that, we just have to remember to double it, because that's the one thing I always forget every time I do this problem. Right? But if we find the limit of this, the limit as n approaches infinity of 1 minus 2n squared plus 3n plus 1 over 6, then we'll have, and then double it, then we'll have our area. All right. So we can break up our limit. Limit of a constant is a constant, but limit as n approaches infinity of 1 minus the limit as n approaches infinity of all of this would be the equivalent expression. So this becomes a 1 minus, oops, sorry, I lost my n squared here. I don't know what happened. Now this is another L'Hopital's rule situation, but I'm already running low on space. And also, this problem's long enough as it is. So what I would say is just kind of do it on the fly, sort of scratch it out on the side. So if I take the derivative of the top and the bottom, this would be 4n plus 3 over 12n, right? And then take the derivative of that, again, top and bottom separately. I'm going to get a 4 over 12, which is a 1/3, right? So just a 1/3. You could also use technology if you want, if I'm being realistic about this. Right? But if you just want to scratch it out on the side, that's fine too, because it's basically the same process we did before for the previous question, just a little bit more, little jazzed up. But then we have to remember to double this. So we take this value, multiply it by 2, and we get, oh, actually, let me not write it like that. Take it and multiply it by 2. Because again, just looking at the Desmos screen here, this only gave us half of the desired area. So we multiply by 2 and we get 4/3. All right. So that's the Riemann sum, also known as the limit definition of integration, right? The limit definition of a definite integral, right? So it gives you the area under the curve, but obviously not in the most efficient sort of way, right? So next class, we're going to get into different shortcuts associated with integration so that we don't always have to do this, right? But we will have to do this. You're just not always going to have to do it, all right? So I'm not going to steal any thunder just yet, but I mean, if you've looked up definite integrals, or if you have any experience with this material, then you already know where this story is going. But there is a connection between this material and that stuff. Like when you start looking at that integration symbol, that funky S, there is a connection there. All right. So, but that's we're going to save that for next class. All right. So that's where I'm going to leave it. Tortured you enough, I think, for one evening. I'm going to stop the recording